Okay, at the beginning of the year, when we were working with evaluating limits, we always started this process of solving a limit by doing direct substitution. And oftentimes, what happened when we performed direct substitution was we encountered an indeterminate form. And the most common one that we encountered was the 0/0 form. And we learned some various methods for solving these limits. This range from solve by factoring, rationalization, and some other methods that we learned. Now, not every problem we encountered could be solved by using those algebraic methods. And today we're going to look at another method to help us solve these limits. And that's going to be L'Hopital's rule. If a limit yields either of the indeterminate forms 0/0 or infinity over infinity, then L'Hopital's rule says that the limit that we have is going to equal the limit as x head approaches the same number of the derivative of the top over the derivative of the bottom. Now, the important thing is, in order to use L'Hopital's rule, we have to show that the limit yields the 0/0 or infinity over infinity form first. Now, there are more than just those two indeterminate forms. There's a bunch of them. However, in order to use L'Hopital's rule, it has to be written in one of those two forms. So you might have to do a little bit of a rewrite in order to apply L'Hopital's rule. And so let's look here at this first example. I want to find the limit as x approaches 0 of e to the 3x minus 1 over x. Well, I do a real quick substitution. And so I look and say, all right, well, what do I get when I put in 0 for x in the numerator? I get 0, and I get 0 in the denominator. We have the 0/0 form. Now, if I'm going to apply this method, and if this is a free response part of the question, the graders are pretty particular over how they want to see this written. And so what they want to see is they want to see that the limit of the numerators, so the limit as x approaches 0 of e to the 3x minus 1 is equal to 0. And the limit as x approaches 0 of the denominator is equal to 0. And so since that happens, since both the limit of the top and the bottom equals 0, now we can say that we're going to do L'Hopital's rule. I'm going to abbreviate. And that rule says that our original problem, so the limit as x approaches 0 of e to the 3x minus 1 over x, is going to equal the limit of the derivatives. So the limit as x approaches 0 of the derivative of the numerator. Well, the derivative of the numerator is going to be 3 times e to the 3x. The derivative of the denominator is 1. Now we perform substitution again, and we wind up getting 3 times e to the 0, so 3 times 1 over 1, which gives us 3. All right, let's look at another one here. So the limit as x approaches infinity of the ln of x over 2 times the square root of x. Now, if we remembered our growth rates, we could use our in-behavior model, but this one could be tricky and maybe we forget how to do it. Now, if I put in infinity and see the behavior, the natural log function is going to continue to increase forever, and 2 times the square root of x is going to continue to increase forever. So I have an infinity over infinity indeterminate form. So we have to show what these limits are. Even though we did direct substitution, we need to show that the limit as x approaches infinity for the natural log of x is equal to infinity, and the limit as x approaches infinity of 2 times the square root of x is equal to infinity. So since that happens, we can do L'Hopital's rule, which says that the limit as x approaches infinity of our regular problem, so the ln of x divided by 2 times the square root of x, is going to equal the limit as x approaches infinity of the derivative of the numerator, which is 1 over x, over the derivative of the denominator. Now, the derivative of 2 times the square root of x would be 1 over the square root of x. And then we'll do some algebraic manipulations here. We're dividing two fractions, so that was going to wind up reducing to the limit as x approaches 0. We'd have the square root of x over x, which I can continue on and say it would be the limit as x approaches infinity of 1 over the square root of x. Now we look at that and we see it's a power function. In behavior model, the denominator is growing faster. Bottom heavy is going to equal 0. All right, looking here, limit as x approaches 0 of 2 tangent of x over 5x. I do real quick direct substitution, see if maybe we get lucky. Tangent of 0 is 0, and 5 times 0 is 0. So we have the indeterminate form. So we're going to write and show that the limits of the numerator and denominator both produce 0. So the limit as x approaches 0 of 2 times tangent of x is equal to 0. And the limit as x approaches 0 of 5 times x is equal to 0. So according to L'Hopital's rule, our original limit, the limit as x approaches 0 of 2 times tangent of x over 5x is going to equal the limit as x approaches 0 of the derivative of the numerator. The derivative of the numerator would be 2 times secant squared x over the limit of the denominator, which would just be 5. Now we do direct substitution. So I put in 0 for x. Secant of 0 is 1. And I still have 5 in the denominator. We get 2/5. All right, let's look at this one here. We have the limit as x approaches infinity of the square e to the negative x times the square root of x. If I put infinity in, e to the negative infinity is approaching a value of 0. And then I have the square root of infinity, which is the square root function is going to increase without bounds. So we have 0 times infinity. That's an indeterminate form. What we need to do is we need to rewrite this problem and see if we can find a way to solve it. Well, I'm going to take the e to the negative x, and I'm going to move it to the denominator. So that gives me the square root of x over e to the x. Now that I have this, I could look at this and I can ask myself, all right, well, as x approaches infinity, we can look at our end behavior models. What's growing faster, the square root of x or the exponential function? The exponential function grows faster. This is bottom heavy, which means that this limit is going to be approaching 0. All right, new one here. Limit as x approaches negative infinity of x squared over e to the negative x. Now, looking at the direction we're going here, if I put in negative infinity, this is going to make e to the infinite power. And we could look at this and just say, hey, wait a minute. I can use my end behavior model and say that this problem is going to be bottom heavy, so it should equal 0. Now, the other previous question did the same thing. Let's go back and let's show that we could also solve this using L'Hopital's rule. So we have the indeterminate form, infinity over infinity. So we need to write our two limits before we apply L'Hopital's rule. So the limit as x approaches negative infinity of x squared is equal to equal to infinity. And the limit as x approaches negative infinity of e to the negative x is also infinity. So according to L'Hopital's rule, our original problem would be the limit as x approaches negative infinity of x squared over e to the negative x is going to equal the same limit, but when applied to the derivative of the numerator and the denominator. So the derivative of the numerator would be 2x. The derivative of the denominator would be e to the negative x times negative 1. We put in and look and see what happens. Well, I put infinity in a way and look at the behavior. So that would 2x would be decreasing without bound, and so would my denominator. And so I applied L'Hopital's rule, and I still have an indeterminate form. Well, guess what? You can apply L'Hopital's rule many times if needed in order to eventually get to the answer. So I would have to do this again. Now, if I went to go do L'Hopital's rule again, I have to state my limits again. So the limit as x approaches negative infinity for 2x is equal to negative infinity, and the limit as x approaches negative infinity for negative 1 times e to the negative x is equal to negative infinity. So we're going to do L'Hopital's rule, and that's going to get, we would say that our limit where we're stuck at temporarily, the limit as x approaches negative infinity of 2x over negative 1 times e to the negative x would equal the limit as x approaches negative infinity. Take the derivative of the numerator and you get 2. The derivative of the denominator, we get positive 1 times e to the negative x. Now we put in negative infinity. The top is always 2. This is definitely a bottom-heavy function. The bottom's going to grow much faster when we head towards negative infinity, and we get 0. Last problem here. The limit as x approaches 0 from the right of x to the x power. Right? And this is a good problem here because we look and see what happens, and we have 0 to the 0 power. That is an indeterminate form. 0 to the 0 is an indeterminate form. Now, this is not written in a manner that will allow me to make it into a rational form or some kind of fraction where I can get a 0 over 0 limit or a infinity over infinity limit where I can apply L'Hopital's rule. So I have to get creative with how I'm going to rewrite this. I'm going to set this limit equal to y. So y is going to equal the limit as x approaches 0 from the right of x to the x power. What I'm going to do is I'm going to try to get the x out of the exponent. So I'm going to apply the natural log to both sides of this equation that we made. So y is equal to the natural log of, the natural log of y is equal to the natural log of the limit as x approaches 0 from the right of x to the x power. Now, we're applying the ln function to this limit. Well, we're looking at as x approaches 0 from the right-hand side. The natural log function is continuous as x heads towards 0 from the right side. It's defined everywhere, just not defined at 0. But it's defined everywhere as we come at 0 from the right. So what I can do is I can take that natural log and I can apply that natural log inside of the limit. So the limit as x approaches 0 from the right for the natural log of x to the x power. Now we're going to use some properties of logarithms. I can take the exponent of that x and I can bring it out front. So I have the ln of y is equal to the limit as x approaches 0 from the right-hand side of x times the ln of x. Okay, now our focus is still just going to be right here. All right, so we're just going to look at that part. Let me change colors here. Go with blue. All right, so we want to solve that limit. Well, that limit that I highlighted is basically as we approach 0 from the right side, we have 0 for x times the ln of x approaches negative infinity. So what we're going to do is we're going to try to rewrite that so that way it's a candidate for L'Hopital's rule. So we have the limit as x approaches 0 from the right. And what I'm going to do is I'm going to rewrite that multiplication by x as the ln of x being divided by 1 over x. So you did skip, change, flip. That would make x times the ln of x. Now we look at what we have after we rearrange this problem in that way. The ln of x would be heading towards negative infinity. And the 1 over x function would be heading towards positive infinity. Now we've rewritten this in a form that is a candidate to use L'Hopital's rule. So what we're going to do from here is we're going to show our two limits. So the limit as x approaches 0 from the right of the natural log of x is equal to negative infinity, and the limit as x approaches 0 from the right for 1 over x is equal to positive infinity. So we're going to do L'Hopital's rule, which says that our limit, so the limit as x approaches 0 from the right of the ln of x over 1 over x is going to equal to that same limit as x approaches 0 from the right of the derivatives of the numerator and denominator. The derivative of the natural log of x is 1 over x. The derivative of 1 over x is going to be negative 1 over x squared. And then what we're going to do is we're going to rewrite that again. We're going to do some simplifying because we still would have infinity over infinity, but I just can clean this up using some algebra. And so you do skip, change, flip, then make x squared, negative x squared over x. And then I could cancel out an x. And we're going to wind up with the limit as x approaches 0 from the right of negative x, which gives me 0. So 0 is not our answer, though. 0 is what that one limit equaled. The limit as x approaches 0 of x times the ln of x. So what we're going to do is we're going to take the natural log of y, which is supposed to equal what we just solved for. So the ln of y has to equal 0. And we're going to solve for y because y is what the answer to our original problem is. And so when we do that, we have to rewrite this in exponential form. So the base of the log raised to the 0 power is equal to the inside of the log. And we get a final answer of 1.